Hello everyone, welcome back to my channel. So in this video we'll see residue, what is residue, and formulas to calculate residue, and also the Cauchy's residue theorem statement. Okay, if you are first time to my channel, please consider subscribing. So residue is the coefficient of 1 by z minus z naught in the Laurent series expansion of f of z about the isolated singularity z is equal to z naught is called as the residue of f of z. Okay, so we know that the Laurent series expansion is given by f of z is equal to summation n is equal to 0 to infinity an z minus z naught whole power n plus summation n is equal to 1 to infinity bn by z minus z naught whole power n. Okay, this already we have seen in the previous videos. So the coefficient b1, bn is given by 1 by 2 pi I integral c f of z by z minus z naught whole power n dz. Right, so if you expand this series, b1 is the coefficient of 1 by z minus z naught. Just substitute n is equal to 1, so here you will get b1, right, here you will get b1, and here you will get z minus 1 by z minus z naught. So this 1 by z minus z naught coefficient, that is b1, is called as residue. So the coefficient of f of z at z is equal to z naught is b1, and from the Laurent series we know that just substitute n is equal to 1 here, so you'll get b1 is equal to 1 by 2 pi I integral f of z dz. Okay, so f of z dz, because z minus z naught whole power n will be cancelled off, so you'll get like this, right? So integral c f of z dz is 2 pi I into b1. 2 pi I just send to the left hand side, so you'll get like this. So 2 pi I into residue of, so what is b1? b1 is called as residue of z f of z at z is equal to z naught. So this formula forms the basis for Cauchy's residue theorem. Okay, so this formula forms the basis for Cauchy's residue theorem. Okay, so that is the thing here. So the coefficient of, the important point you have to remember about the theoretical point of residue is the coefficient of 1 by z minus z naught in the Laurent series expansion is called as residue. Okay, this is the only point which you have to remember. Okay, so this is the only theoretical introduction of residue. Okay, so just keep in mind that the coefficient of 1 by z minus z naught in Laurent series expansion, okay, is called residue of f of z at z is equal to z naught. This is the only important point which you have to remember from this theoretical concept. Okay, so let me take another slide, and I will explain you clearly the formulas used to calculate the residue and also the statement of Cauchy's residue theorem. Okay, right, next we'll see the formulas to calculate the residue. Okay, so only 5 points you have to remember, right? So only 5 points you have to remember. I'll write now each and every point and explain you clearly. Okay, so if you can remember all these 5 points, then you can solve any problem regarding Cauchy's residue theorem and calculation of residues for a given function f of z. Okay, so first point is residue of simple pole. Residue of a simple pole at z is equal to z naught is given by residue of z at z is equal to z naught is equal to limit as z tends to z0, z minus z0 into f of z. Okay, this is the formula to calculate the residue of f of z at z is equal to z0 when it is a simple pole. Okay, that means pole of order 1, right? Next, residue of pole at z is equal to z0 of order m. Okay, of order m is given by residue of f of z at z is equal to z0 is equal to 1 by m minus 1 factorial into limit as z tends to z0 dm minus 1 by dz m minus 1 z minus z0 whole power m into f of z. Okay, so this is your formula if the pole is of order m. Okay, suppose if you have z to the power of 4 by z minus 1 z minus 2 whole to the power of 4 into z minus 3, right? If you have a function f of z of this form, so z is equal to 1 is called as simple pole. And if you are asked to find the residue at z is equal to 1, you have to use this formula. And z is equal to 2 is a pole of order 4. Pole of order 4. And if you are asked to find the residue at this point, that is z is equal to 2, then you have to use this formula, the second formula, right? So based on the pole, right, if it is a simple pole, you have to use the first formula, and if it is a pole of order m, you have to use this second formula. Okay, next, third, if f of z is of the form phi of z by psi of z, that means it is the function of two so f of z is a function of two different functions, that is phi of z and psi of z, phi of z in the numerator and psi of z in the denominator. And at z is equal to z0, if two conditions has to be satisfied, that is phi of z0 should not be equal to 0 and psi of z0 is equal to 0. These two conditions has to be satisfied. So if these conditions are satisfied, then residue of f of z at z is equal to z0 is given by phi of z0 by psi dash of z0. Okay, just remember this formula, very very important. Phi of z0 by psi dash of z0. Okay, so if it is a function of two different functions, phi of z in the numerator and psi of z in the denominator, and at z is equal to z0, two conditions has to be satisfied. So phi of z0 should not be equal to 0, because if this is equal to 0, then f of z is equal to 0, and psi of z0 is equal to 0, then residue is given by phi of z0 by psi dash of z0. That is differentiation you have to find. Okay, next, fourth formula, residue at infinity. Okay, sometimes they may ask you residue, find the residue at infinity, that is at z is equal to infinity, that means z0 is equal to infinity. Okay, which is not a finite quantity. So when you are having a finite quantity, you have to remember these formulas. So residue of f of z at z tends to infinity, that is at z is equal to infinity, is equal to minus coefficient of 1 by z, minus coefficient of 1 by z if f of z has infinite terms. Okay, if f of z is having infinite terms, then residue of f of z at z is equal to infinity is minus coefficient of 1 by z. Okay, suppose for example, okay, let me write one more formula. limit as z tends to infinity. So this residue of f of z at z is equal to infinity is also equal to limit as z tends to infinity minus z into f of z, minus z into f of z if f of z is analytic function, if f of z is analytic function. Okay, so this is the thing here. So these two formulas you have to remember. So if f of z is analytic function, this will be the residue formula. Okay, so if f of z has infinite terms, this will be the residue formula. Okay, so suppose if you have sine of 1 by z. Okay, so if you expand this sine of 1 by z, what you will get? 1 by z minus 1 by z whole cube by 3 factorial plus 1 by z whole to the power of 5 by 5 factorial minus 1 by z whole to the power of 7 by 7 factorial plus so on. Okay, so if you are asked to find residue of this f of z, that is f of z is sine 1 by z at z is equal to infinity, then its value is equal to 1 because the minus 1 because the coefficient of 1 by z, because it contains infinite terms, yes or no? So it extends up to infinity, so it has infinite terms. So when you have infinite terms, then coefficient of 1 by z represents the residue at z is equal to infinity. So 1 by z, coefficient here is 1, so coefficient here is 1, so it is minus of this coefficient, so it is equal to minus 1. So residue of f of z at z is equal to infinity is equal to minus 1. Okay, this is how we can calculate residue at z is equal to infinity, right? So in the upcoming videos I will take more problems on each and every concept and each and every formula which I have written here. Okay, so there I will explain you clearly how to find the residues. Okay, so until then, please remember all these formulas. Last one is Cauchy's residue theorem. The last point which you have to remember is Cauchy's residue theorem. So if f of z is analytic function, right? So if f of z is analytic function and z1, z2, z3 and so on up to zn are poles within a closed contour C. Okay, within a closed contour C. So if these are the number of poles within closed contour C and their corresponding residues are R1, R2, R3, so on up to Rn. Okay, so based on the poles, so if the pole is simple pole, you suppose z1 is a simple pole, then you can calculate the residue using this formula. So that residue I am considering it as R1, and if z2 is a pole of order 4, then you can find this residue, its corresponding residue R2 by using this second formula. Okay, so likewise if you have n poles like this and you have calculated n residues like this, then according to Cauchy's residue theorem, integral C f of z dz, that is if you want to evaluate the integral, okay, then it is given by 2 pi I into sum of residues, 2 pi I into sum of residues. Okay, so that is 2 pi I into summation n is equal to 1 to n Rn. 2 pi I into summation n is equal to 1 to n Rn. So you have to find the individual residues. Okay, so at each and every pole, okay, so important point is it should be within the closed contour, right? So first of all you have to check whether the pole is inside the contour or not, right? So, same procedure which we have followed for Cauchy's integral formula also, we have followed the same procedure. The first thing we have to see is we have to check whether the poles z1, z2, so on up to zn is inside the contour or not, inside or outside the contour. First of all, you have to check this. So if it is inside the contour, if any pole is inside the contour, then calculate the residue using the first two formulas or first four formulas. You can use any one of the formulas. You can use any one of the formulas and calculate the residue only when the pole is inside the given contour C. Inside the given contour C, if the pole exists, then you have to calculate the residue using any one of the first four formulas. Then after calculating the residues at each and every pole, the integration of f of z dz over that closed contour is given by 2 pi I into sum of residues. 2 pi I into sum of residues. Okay, so this is called as Cauchy's residue theorem, right? So with these formulas, you can solve any problem based on residue theorems and calculation of residues when a function f of z is given. Okay, so in the next videos, in the next upcoming videos, we'll solve problems based on these formulas. Okay.